Can you guys hear me all right out there? Okay, we're we're at about 11, so we'll just go ahead and get started. So our agenda for today is I'll talk about an AQ stop, start, continue activity that I just posted in Canvas as part of your professional development points for the course. I'll talk about interim grades that have been posted in SOAR for today for your advisement for spring semester. Talk about a little bit of the class stats. We'll review the functional group acidity and pKa table. So that main sort of understand in this chapter. We'll look at a couple different molecules of ciprofloxacin, albuterol, and morphine. We'll go through some problems for each of those, and if we have time left over, we'll do some questions from the workbooks. So let me do the following. Can we get, I still don't know how to do this. Can we get everyone to mute their mics? Because there's a little bit of feedback. If you don't mind. Okay, so let's look at, let me just tell you what AQ is. It's the Association of College and University Educators. So I went through a 3-semester sequence here at USM for basically learning how to incorporate active learning techniques into lectures. And so one of the activities that we learned about was the stop, start, continue. So this is typically given at mid-semester. So since interim grades are due today, I posted an assignment in Canvas where you're given 3 prompts: stop, start, and continue. And so basically it's pretty self-explanatory. You need to write anywhere between 3 to 5 sentences for each. And you'll submit this in Canvas as a Word document, and it's worth 6 points. So 2, 4, 6. 2 points for each, 6 points total. So what do you wish we would stop doing in class? What do you think we should start doing? And what is working well for you? Again, in the virtual teaching environment, this is a little bit different than normal. So I expect you to be honest, really, and really let me know how this learning experience can be made better for you. And again, that's in Canvas. Again, if you have any questions, shoot it in the chat or send me an email. So if you check your SOAR account, your interim grade will be posted for this course and every course. So normally what I would do, I would have everyone's ID, their actual grade, and then their rank in the class, like shown on another slide. But since we're sort of different, I'm just giving you the overall class stats. So at the interim point here, there's 289 points, and this is just for modules 1 and 2 so 289 of the total 800 course points. So if the semester were to end like right now, 21 people would get A's, 62 people would get B's, 36 would get C's, 17 would get D's, and 24s would get F's. So that's the actual letter grades. The percentage of that, so all of these numbers divided by 160, so 13% for A, 39 for B, 22 for C, 11 for D, and 15% for F. So again, the thing to understand about this course is that it is not graded on a curve. You are not competing with anyone else in the class. You are essentially just accumulating as many points as you can up to 800. So there have been some questions about bonus points, and I'll consider those type of activities, you know, on the sort of end part of the semester as we learn more about the grade distribution. But there it is. If you have any questions, again, shoot me an email. Maybe I can just take a informal poll, just a yes or no in the chat. Would you want me to create a column in Canvas that tells you your rank out of 160 students in the class? Is that something you're interested in knowing? Yes or no? So Hannah asks about exam averages. I know that's a common thing students like to know. I really don't like sharing that information publicly because I don't really think it's relevant to you as a student in your learning experience. I know you've been conditioned over the course of your educational experiences to compare to the average. I don't think it's helpful for you to know that number, so I really don't post it or share it publicly. I know that's probably not what you want to hear, but I really think the rank is a better indication of, you know, it is sort of competitive, but it tells you so how your performance relates to your peers a little bit better than, like, say, an average would. So I would say the responses are all equal, yes, no. So maybe we'll just skip that. Let's go ahead and get started. So the main thing for chapter 3 is we're learning about acidity, and we really want to be practical about it. So we've learned how to determine unique types of hydrogen sets in a molecule. And what we did last chat session was then associate those sets with a type of functional group. Then we can identify that functional group as an acid on this table and quantify it according to a number. So the pKa number, the higher, more positive that pKa number is, the weaker the acid. The lower and more negative the pKa number is, the stronger. So the relationship between acid and base, so acid conjugate base, is inverse. So for example, this species here that has a pKa of -12 is a very strong acid, but a very weak conjugate base. So on the flip side, this sp3 hybridized carbon H bond is a very weak acid, but its conjugate base is the strongest conjugate base on the scale. So that's qualitatively, you should be able to understand that difference. Then, as I said, try to just put the functional groups in bins of, say, 5. So you have your -10, your -5, your 0, your 5, your 10, 15, 20, 25, 30. So if you categorize that, sort of understand these functional groups a little bit easier than memorizing specific numbers. So we're going to use this table in our questions. So let's open up. You want to get your cameras out, snap a pic of this QR code for ciprofloxacin. We'll look at cipro in relation to acidity, and I'll ask you a bunch of questions. So Carly asks, I worked at Pfizer by virtue of they sort of acquired the company I was working for. So it's sort of like I wasn't really hired by Pfizer. I was just as part of their merger and acquisition. And so I was retained with that company for about a year before I was laid off, as they say, or Pfizered. So that was an interesting experience in life, to say the least. So here is ciprofloxacin, and Cipro is produced by Bayer. So Bayer is a chemical company. You've probably heard of them. So they have a pharmaceutical division, and Cipro is a broad spectrum antibiotic. And here's the structure. So here is sort of a little movie of that space filling model moving around. So when I look at this, I say to myself, wow, that molecule is relatively flat. So how do we understand the flatness? Well, look at all these sp2 hybridized carbons here. So again, sp2 hybridized carbon is trigonal planar. So it sort of makes that scaffold flat. Then you have this ring here, which is shown sort of there. That is torqued a little bit. It gives it some sort of three-dimensionality to it. But at this point, you should be able to identify a lot of functional groups. And so we're going to, over the next couple questions, look at unique types of hydrogens, classify their functional groups, rank their pKa's. Cipro was I think touted when avian bird flu was a thing, you know, back in, say, 2005 to 2007 as being a broad spectrum antibiotic. So these antibiotics have different classes. This is called a fluoro. There's the fluorine fluoroquinolone. And if you go on to take biochem or pharmacology, toxicology, you'll learn the mechanism of action of how these things work based on the functional groups present. So let's consider this question: which functional group in ciprofloxacin has the most acidic hydrogen? So here are your choices. The functional groups, which one has the most acidic hydrogen? So yeah, the correct answer is C, the carboxylic acid. So again, how do we know that? We go to our table here. One thing I might point out to like make the mental burden of making it through this class easier. Again, you're just looking for this part of the acid. So really that's sort of right here. So we're going to learn what happens when you vary this part So this is ethanoic acid. There's the carboxylic acid functional group. We'll look at when you start changing this, what happens to this number. But in general, it's about 5. So all the other functional groups that were listed have a higher pKa value. So which functional group in Cipro has the least acidic hydrogen? So least acidic, meaning which, if we corresponded that to a pKa value, it'd be very, very large and positive. So B as in boy is the correct answer, alkane. So I've pointed out a couple hydrogens here. So like amine, alkane, alkene acid. So this would be the alkane type, sp3 hybridized carbon, H. Again, you don't see that specific thing on this table, so you relate it to something that's as close as possible, and that would be this molecule here, ethane. So you see it's at about 50. So what does that really mean? And we'll learn about when we're ranking things from most to least acidic. If something's very acidic, that means you can use a weak base to remove the hydrogen or the proton. If something is not very acidic, the hydrogen atom / proton, we use those terms interchangeably. You have to have a very strong base to remove this hydrogen. So again, that's the inverse in the acid-base thinking that we want to understand. So here's a typical problem that you would see in terms of ranking those hydrogens. So there's 4 hydrogens, each identified with a Roman numeral. And it's asking you to rank the acidity from the weakest to the strongest. So again, I think probably the thing that confuses students with this is like that sort of less than, greater than. Again, this order, the weakest acid has to be listed first, or to the most left. The strongest acid has to be listed last, or to the most right. And then sort of what that less than symbol means. So yeah, it should be D as in dog is the correct answer. Again, if we were to quantify this, so the alkane is about 50 in terms of the pKa. The alkene is about 35. The amine, or sorry, the alkene is 45. The amine is 35, and then the acid is 5. So you're associating not only like the look in terms of the bond line representation of the molecule, so how this looks with the word alkane, with the pKa number, and then you can sort of rank them, however you want to think about the concept. Any questions before we move on to another example of albuterol. So here is another molecule, albuterol, and this one's nice because we have some different functional groups. So here's the bond line representation. This is a ball and stick. This is the space filling. So this is sold as Proventil or Ventolin. So here's what is typical in a sort of delivery system called an inhaler. And so albuterol is a bronchodilator for asthma or chronic obstructive pulmonary disorder. So pulmonary is your lungs. So it's basically the little alveoli or whatever it's called in your lungs. If they sort of close, this molecule helps open them up so it can sort of harvest oxygen out of the air. If I can just maybe make a point here, what is challenging, I mean, people, you probably know about inhalers, right? But really the technical challenge of these type of drugs is delivering the molecule in an aerosol form. So if you think about that, you're squeezing that thing and it's ejecting the molecule. So the molecule has to get into the lungs. So it can't be in solid or liquid form. So scientists like at what company is this, Schering-Plough, as you see on the box there. So the scientists, the physicists, chemists, they have to develop a system that's going to aerosolize that compound, and that's not as easy as you might think it is. Because if you really look at the structure, what have you learned so far? You have hydrogen bond donor acceptor groups, right? So if those things are attracted to one another, the molecule might just want to stay in liquid or solid form. So how do you overcome that? What other dispersants do you have to add to this little canister to get it into the lung so it can function properly? So let's consider some questions here about albuterol. So this one has CHs, OHs, and NHs in different functional groups. So what is the most acidic hydrogen in albuterol? When I give this question on an exam, students get a little confused. The choice that you're looking for, so there's A, B, C, or D. So that's what you're looking for in terms of your response. So let me ask you this. We sort of touched upon this this past Wednesday in the chat session, that generally speaking, CH bonds are less acidic than heteroatom H bonds. So we can sort of see that HB should definitely be less acidic. So that leaves us A, C, and D. But look at, you have HC and HD, or excuse me. So HC is bonded to, that's carbon, excuse me. If I would have said, instead of HC being here and HC was there, those are both alcohols, right? Why would HD, this one, be more acidic than this one, do you think? So the question is, if instead of having HC bonded to carbon, if this was HC, you have OH and then OH. What differentiates those two alcohol functional groups? So a couple of the initial responses in the chat, it's basically the one oxygen is bonded directly to the ring. And so that definitely increases the acidity quite a bit. So let me point out in the table. So your typical alcohol. So this is sort of your typical alcohol here, as is this. You know, that's at about the 15 to 18 range here. If we scroll up on this table, C6H5OH, so that's a benzene ring, there's OH. So it drops the acidity quite a bit. And so as we've seen in the chat, that difference is associated with the presence of the benzene ring. So let me just turn the doc cam on and show you what we mean by resonance and why that's more acidic. I'm gonna use like just sort of two very broad examples. So here's sort of one example where the OH is bonded to a ring, and then this would be like ethanol, where the OH is just bonded to an sp3 hybridized carbon. So if you were to treat this molecule with, say, a base that you're familiar with. So this is sodium hydroxide. And we know that this is a base. So this has to be an acid, right? So we have an acid-base reaction. So how do we show this hydrogen being removed? So a base will supply electrons to abstract a hydrogen. So the way that happens, the way we show that is, so see the electron pair here, it doesn't matter which one, but we're going to start at the electron pair. We're going to draw an arrow that points to this hydrogen. And the reason it points to that hydrogen, again, is based on electronegativity. So that lone pair of electrons is abstracting that hydrogen. We're going to form an OH bond. So that's what that means. These two electrons are forming a new bond. We know that hydrogen can only have one bond at a time, so then this bond has to break. So notice the flow of these arrows. When this bond breaks, these two electrons are pointing, sorry, I drew this wrong. That should be plus and that should be minus. Taka, thank you for pointing that out. So the electrons in this bond are pointing to the delta negative. So this oxygen is accepting the two electrons. So when we draw the products of this, this oxygen now has a negative charge. The sodium is a spectator ion that balances out the negative. And we're ending up with a molecule of water. So we have acid base, then over here, this is the conjugate base, this is the conjugate acid. So let me just show you the same reaction down here, why this case is special, this alcohol. So if this is the base, this is the acid. So conjugate base, conjugate acid. So notice I drew this arrow and then these different. So let me click back on this table. We said that this molecule has a pKa of about 10. Ethanol has a pKa of 16. Water has a pKa of 15.7. So the reason that this is a stronger acid than this is due to, as we said in the chat, this negative charge can be delocalized into this ring through resonance, where this negative charge is solely located on that oxygen. So because this has a more acidic pKa, when we treat with this base, it fully goes 100% towards the products. And we rationalize that by comparing these two numbers, 10 and 15.7. This equilibrium lies towards the weaker acid-base pair. In this example, because 16 and 15.7 are essentially the same, the forward and reverse reactions happen equally. And so to show you why this species here is more stabilized due to resonance, the negative charge can come down. So here's a resonance arrow. So this is a reaction arrow, equilibrium arrows, resonance arrows. So in resonance, the negative charge moves from oxygen down to carbon. We can draw more such resonance forms. That further show how this negative charge moves around. And the more you stabilize it, it's a way of thinking about how this is much more acidic than this, where this negative charge is only located on that single oxygen. So is this concept clear about why we're claiming that even though we have OH and OH, why one is more acidic than the other, using some of the concepts from that table? How do we know if it's more or less acidic than water? So Mac is asking, how do we know if it's more or less acidic than water? So again, I hate to use the word memorize, but you really have to familiarize yourself with these functional group representations in this column and what the associated pKa values are. So you're really looking for what is the best representation of sort of that functional group. So again, in this molecule albuterol, this question is asking you, what is the pKa of the most acidic hydrogen? So again, you have alkane CHs, you have an amine NH, you have alcohol OH, and then this alcohol OH. So the alcohols are differentiated from one another in that this one is attached to the ring. And so it becomes more acidic due to this resonance that we've shown. So the correct answer for this one is A of 10. And again, we find that by looking on this table, C6H5, that's what this is, 6 carbons, 5 hydrogens, and then your OH. So that is the condensed representation of this. So given given this new slide that's up, it's asking you what is the least acidic hydrogen in albuterol. So here's HA. Classify what functional group that is. Here is HB. Here is HC. And then here is HD, which we already said D was the most acidic. So C is going to be the most, or excuse me, the least acidic, because that's an sp3 hybridized carbon, H bond, so that's more like an alkane with a pKa of 50. So that gets to this next question here, which we just said. I removed sort of all the implicit hydrogens, and it's asking you the least acidic hydrogen. So any of these that are bound to an sp3 hybridized carbon will have a pK of 50. So these hydrogens here, these two, this one, these two, these on the methyls, we can broadly classify those as all alkanes. They'll all have pKs of 50. questions on that before I flip to some other slides regarding acid-base reactions? Okay, let's consider the slide that's up now. It says, in the following acid-base reaction, what is the relationship between the boxed molecules? So yeah, they're definitely best friends forever. For sure, for sure. So the scientifically correct answer would be B as in boy. So it's acid conjugate base. So once you figure that out, the other pair is then the base conjugate acid. So here's a follow-up to that. In the following acid-base reaction, the boxed molecule is functioning as what? And the product should have which charges on the heteroatoms? So the molecule in the box on the reactant side is functioning as what? Then if you look on the product side, you have some heteroatoms that are not currently, as they are drawn, obeying correct Lewis guidelines. So they should have a formal charge associated with them. What should those charges be? I can't tell if people have responded yet. So it's definitely not A or C, because the first fill in the blank thing there says acid. So we're stuck between B and D. So again, the formal charge part is, again, if you're considering that the heteroatom is no longer in its neutral state, what should the formal charge be if nitrogen is gaining a bond and oxygen is losing a bond? So I see more D as in dog answers than B at this point. So D is the correct answer. So what I've shown on the document camera is that reaction, and let's sort of walk through how this reaction takes place. So from an empirical or sort of observational first principles viewpoint, you can see this molecule. It's essentially a benzene ring where one of the CH groups has been replaced with nitrogen. So what is the sort of typical valency for nitrogen? You can obviously see 1, 2, 3 bonds. So what's the last thing this nitrogen has to have? So a lone electron pair, and I'm going to draw that right here on the document camera. And then I'm just going to fill in these lone pairs on oxygen. So again, nitrogen in the neutral form has 1, 2, 3 bonds, 1 lone pair. Oxygen, 2 bonds, 2 lone pairs. So you see a couple different ways of oxygen based on its functional group. So if you just look at what's happening at this nitrogen atom here, it is gaining a hydrogen. And where is that hydrogen coming from? It's coming from this acid functional group. So because you know this is a carboxylic acid, and these things always come in pairs, this has to be the base. So this is the base, this is the acid, this is the proton that's transferred. And now these heteroatoms look different than how they did over there. So how does this hydrogen move from here to there? So the way we demonstrate that in organic chemistry is called the arrow pushing formalism. And what do we mean by this word formalism? If you could shrink yourself down really, really tiny on the molecular level, you would not actually see an arrow moving. So this is a way for us humans to mentally keep track of the movement of electrons. So this lone pair of electrons on nitrogen is acting as a base. The function of a base abstracts. An acid donates. So these things always occur in pairs. This base, lone pair, is abstracting that hydrogen. Notice the way I drew that arrow moving. It starts at the lone pair and it points to the hydrogen. This is the quarterback throwing the football to the receiver. We know that hydrogen can only have 1 bond, so this bond here has to break. The next arrow starts in the middle of this bond. Those 2 electrons move on to oxygen. The arrowhead points to the delta negative. So if oxygen had already had 2 lone pairs, it's now getting the 3rd lone pair. So it's going to have a formal negative charge. this hydrogen, the lone pair is now tied up in this bond, so it has a positive charge. So let me say, in the arrow pushing formalism, see how you're starting neutral? There's no charge, no charge. You're accounting for plus and minus. So even though you're generating these charges, they must balance each other out, plus, minus. So overall, it's still net neutral. So James asked, well, the conjugate base, so this is the acid, this is the conjugate base, will it always have a negative charge? No, it will not. The reason that it has a negative charge here is because here you're starting neutral, neutral to negative. If you were starting with an acid that was positively charged and a hydrogen was removed, the conjugate base would be neutral. So really, that's why you have to pay attention to your what's acting as your base, what is your acid, in any pre-existing charges. So I want to do some problems from the workbook just to follow up on this arrow pushing, because this formalism is how you need to think about how not only acid-base reactions happen, but all reactions in this class. So acid-base reactions are a subset of reactions. We will use the arrow pushing formalism in all our reaction mechanisms. So it's important to know that the base does the job of abstracting, the acid does the job of donating. So let me put up the workbook. This is page 56 in the first semester workbook. Let's look at example problem chapter 3, number 38. Show a mechanism for the following acid-base reactions. So when you look at these two species, which one is the acid and which one is the base? So we're looking at problem 338. We want to show how the proton is exchanged. Maybe that's not, well, I'll say this is 1, this is 2. Is 1 the acid or the base? So 1 is the base, 2 is the acid. See this negative charge? What that means is the carbon has a lone pair on it. So if it's acting as the base, water is the acid. So the negative charge is attracted to the partial positive. There's only one type of hydrogen in water, right? So it doesn't matter which one of these we abstract. The arrow is starting at the lone pair. It's pointing to the hydrogen, which is positively charged. Notice here in the product, it's neutral. Hydrogen can only have one bond, so this bond has to break. The arrow points towards the oxygen. Now the oxygen in the product side has 3 lone pairs, so that's how it gets its negative charge. So 339 is sort of more of the same, where 1 is the base, 2 is the acid. It's just a different source of a hydrogen here. So the electrons on that carbon, delta plus, nitrogen, delta minus. So we're abstracting that hydrogen. We break the NH bond, the lone pairs go on nitrogen. The nitrogen now has 2 lone pairs and a negative charge. Is the way these arrows are drawn, does that make sense to you? The arrow is showing you the movement of the electrons. So this carbon bonds to that hydrogen. This HO bond then breaks with that lone pair now going on to oxygen. So pay attention to how the arrows flow. So in this example, in both of these examples, the flow is like this. So you should never draw something like this, because it doesn't make sense in terms of the convention. You should never have 2 reaction or electron movement arrows pointing at one another. So it's the start, the arrowhead, which is the end, the start, the arrowhead, which is the end. The way this is drawn here, that implies that you have 4 electrons basically converging on the same point. And what we know about charge, you can't have negative charges going towards one another. Any questions on this before we sort of flip back to earlier parts in the workbook with our last couple minutes here? So Carly's asking about some Wiley plus issues with drawing the arrows. Again, your arrows, they have to have sort of that flow to them. And I know Wiley Plus sort of draws these arrows for you, and that there can be some sort of technical issues with that. So let's consider problem 334 on page 55, and I'm going to put the table back up. So the table of acidity is back up on the main slide. It says predict the position of the equilibrium for the following reactions. So 334. So I've just wrote some numbers, 1, 2, 3, 4, so that we can communicate with each other about this. On the reactant side, 1 and 2, which one is the acid and which one is the base? So Aiden and James say 1 is the base, 2 is the acid. Now on the product side, which one's the acid, which one's the base? So you're looking at 3 and 4. So 3 is the acid, 4 is the base. Now that you've identified that, I'm gonna circle them. 2 and 3. So when you're doing this sort of problem, now you need to identify, okay, this is an alcohol, right? This is an alkane. Now go to the table that's shown in what is the pKa of this alcohol. I know we're a bit out of time, but let's just finish up the logic for solving these. We've identified the acids. We've identified their functional groups. Now we're looking at pKa's. So James says alcohol is about 15. That's the pKa value. What about alkane? So between 15 and 50, these are the numbers you're comparing. Compound 2 or 3, which one is the weaker acid? Compound 2 or compound 3? So we're getting some responses of 3. 3 is the weaker acid. So the position of the equilibrium lies towards the weaker acid-base pair. The way we generate, or the way we signify that with this type of arrow, it's pointing more there, and then we just draw a little bitty arrow on the bottom. So this sort of designation tells you the equilibrium lies to this side. And we can rationalize that because, as we said on the table on the slide deck, the alkane this is a really strong base. This is fairly acidic. This carbon wants that hydrogen. It abstracts it. We generate a really weak acid with a pKa of 50 and a better stabilized base. So that's how you figure out these sort of problems. Identify the acid on each side, what functional group it's part of, what the pKa is, and then you're looking at the difference. Again, the larger this number, the weaker the acid. So we're about out of time. We're over time actually for today. If you have questions or concerns, please shoot me an email. We can set up a Teams meeting. Try to start working on your Wiley Plus assessments in those professional development activities. But otherwise, we'll check back in for Monday's chat session. So we'll see you then. Have a great weekend.